I welcome you all in this course on steam and gas power systems. Today we will discuss the centrifugal compressors. The compressed air in mechanical engineering applications is often required, and centrifugal compressors are used in the gas turbines. So, it is imperative to discuss them here. We will start with the working principle of centrifugal compressor. Then we will draw velocity diagram, how much work has to be supplied to the centrifugal compressor, we will drive the formula for that. There is this phenomena slip factor, we will discuss the slip factor, pressure rise in a centrifugal compressor, and we will do one worked example. As I said earlier, the compressed air is required in variety of mechanical engineering applications. There are two types of compressors. One is reciprocating compressor, three types in fact: reciprocating compressor, and they are known as positive displacement compressors. Positive displacement compressor, and another type is centrifugal compressors. And third one is axial flow compressors. And these are known as dynamic. Now, positive displacement compressors are used where high pressure ratio is required, but the mass flow rate is not very high in reciprocating compressors because they work on slider crank mechanism. There is a slider crank mechanism as in the case of IC engines. So, there is a crankshaft, connecting rod, and there is a piston which does to and fro motion in a cylinder, and at the end or at the head there are valves. If I draw a vertical diagram of a vertical compressor, so head is having two valves. They intermittently open and discharge the gas or air to the supply pipeline. And if I draw the pressure and volume PV diagram for a reciprocating compressor, it is going to be like this, from state 1 to state 2, then state 3. Now, here the volume at state 3 is shown as 0. But practically it is not possible. I mean, there has to be some clearance between the top dead center and the cylinder head. Otherwise, breakage may take place or some wearing may take place. So, instead of having volume at 3.0, some volume is left 3. That is known as clearance volume, right? And since clearance volume is there, this is at the end of the stroke, right? So, the process starts like this. The piston starts moving in upward direction. Both the valves are closed. So, it is a closed system. So, process 1 to 2 takes place in a closed system. Now, process 2 to 3, when piston has traveled certain distance, now initially both the valves are closed. One of the exhaust valve will open, and pressure will be the gas will be released from the piston. It is a constant pressure process for open system, right. So, in fact, the volume is reducing, and in fact, the mass flow rate is taking place across the system. That is why the volume is reducing. So, up to this is the entire stroke 1 to 3. So, part of the stroke the system remains the closed system, and the part of the stroke the system becomes the open system. At the top dead center, the outlet valve is closed and inlet valve is open, but because the pressure is high, this gas available at state 3 is expanded to state 4, and from state 4 the suction starts. From state 4 the suction starts, then inlet valve will be opened, the fresh air will come in, both the valve will close, then compression, outlet valve will open, the high pressure gas will leave the cylinder, and then outlet valve will be closed, inlet valve will be open, then the expansion of gas takes place. In return stroke, here the inlet valve will open and the air will be breathed into the cylinder. Now, here in this case, because it is a reciprocating machine working on the cylinder crank mechanism, we cannot go for very high RPM. We cannot go for very high RPM because this is not totally balanced. There are certain unbalanced forces in this mechanism, and if you go for very high RPM, unbalanced force will be very high. So, these type of compressors are used where pressure ratio is very high and mass flow rate is low. Low mass flow rate, high pressure ratio. RPM of these compressor is approximately say 1000 RPM or 800 RPM or 1200 RPM. Now, if you take the centrifugal compressor, it is a rotodynamic machine. It is a rotary compressor. In a rotary compressor, there is a shaft. On the shaft, an impeller is fixed and there is a housing. So, there is no unbalanced force. So, these type of compressors, they can go up to say 30,000 RPM, right. In centrifugal compressors, because I will explain you the mechanism later on, there is an axial entry of air and radial release. So, along the shaft there is an axial, the air breathes into the compressor in this axial direction and it leaves the air leaves the compressed air leaves the compressor in radial direction. So, there is a change in direction. In axial flow compressor, the flow is only in axial direction, right, because there is no deviation in the direction. So, efficiency of the axial compressors is the highest, followed by centrifugal compressors, and reciprocating compressors have low efficiency. Say reciprocating, normally reciprocating compressors, they have efficiency of the order of 75 to 80%. It varies between 70 to 80%, 80, 85, or it may go up to 85%. But these compressors have efficiency more than 90%, 90 or 90%, 90 or 90 or more than 90%. Now, in centrifugal compressors, now we will discuss in details about the centrifugal compressors. Now, the elements of a centrifugal compressor is, first of all, there is an inlet pipe which is connected. Suppose there is shaft, right. First of all, I will draw the end view of centrifugal compressor. It necessarily has one impeller, that is very important part of a centrifugal compressor. It is a disc, impeller is nothing but a disc, and disc is mounted on a shaft. Disc is mounted on a shaft, right, and it has vanes. The number of vanes may differ, it is 15 to 20 vanes, and vanes are diverging passages, right, and vanes are surrounded by the diffusers, because when the air enters in axial direction, the compressor is rotating with certain RPM with the help of a motor, because in compression external energy is required, external work is required. So, a motor is fixed. So, motor moves the compressor, right, with a certain RPM, right, and when the fluid enters this impeller, I will draw the end diagram also. It is something like this. There is a housing, inside the housing there is impeller, and impeller is having the vanes. I will draw with a different color. Impellers are having the vanes. So, when this disc is moving, and it can have entry from both the sides. The impeller can have entry of air from both the sides. It can have entry from one side or it can have entry from both the sides. Now this impeller, when the air enters this impeller, so air has, because it is already moving with very high rotational speed, this energy is imparted to air. Air also starts moving with a very high velocity. Now if you look at the first law for open system, first law for open system says that dH plus V dV plus G dZ is equal to 0, or H2 minus H1 plus V2 square minus V1 square by 2 plus G Z2 minus Z1 is equal to 0. Right. Now, when high velocity, this H1 and H2, right, it is delta P by rho, VdP. So, the kinetic energy is imparted to the gas. So, physically if you look at the working of the centrifugal compressor, the air is coming in contact with the impeller and kinetic energy is imparted to the air, right. Now, the kinetic energy from impeller is imparted to the air, then air moves in outward direction, right. Then this energy, kinetic energy is converted into the pressure energy in a diffuser. So, there are two types of diffuser, one is vaneless diffuser, another is vane diffuser. So, when air enters the vane diffuser, it is also a diverging section. When the air enters the vane diffuser, the velocity is reduced and the pressure is increased. And after the vane diffuser, there is a volute casing of increasing the cross section. This is increasing, and at the end of the volute casing, there is exit. So, in a nutshell, initially the air is sucked into the compressor, kinetic energy is imparted by the impeller. Now, this kinetic energy is converted into the pressure energy in vaneless diffuser, vane diffuser and volute casing, and it goes out of the system. Now, if we draw the enthalpy entropy diagram for centrifugal compressor, instead of temperature entropy, if we draw, it is more of the same thing. If we draw enthalpy entropy or temperature entropy, enthalpy and entropy diagram for a centrifugal compressor. So, initially the air is sucked in. So, air is available at state 1, it is sucked into the compressor. So, the pressure at the suction of the compressor is below the atmospheric pressure, only then air can be sucked in, and it is not an isentropic process. So, we can say the process is 1 to 2 or 0 to 1. This is entry to the compressor at reduced pressure. Now, in the impeller, the enthalpy is increased, right. Enthalpy is increased and the air enters with certain relative velocity, right. Now, here in compressors, machine is already moving with very high velocity. So, relative velocity at inlet is higher than the relative velocity at the outlet. In turbines, it is reverse. So, in turbines, normally relative velocity at outlet is greater than relative velocity at inlet. But here, because work is being done on the fluid, in turbines the work is done by the fluid, but here is work is done on the fluid. So, relative velocity as inlet is higher than the relative velocity at outlet, and that is why these passages are made diverging. So, the relative velocity is reduced at the outlet of impeller, right. And if you notice in turbines, in axial flow turbines, we have considered U as constant, pi dn by pi dn, and is it is U is equal to pi dn. If it is an RPM, then it is 60, pi dn by 60. But here you can see it is moving in a radial direction. In turbines, it was moving in axial direction. In Parsons turbine or De-Lowell turbine, it was moving in axial direction. Now, the fluid is moving radial direction. So, peripheral velocity is also changing. Peripheral velocity is changing means kinetic energy is also changing, right. So, it has two components in impeller. Then there is a change in relative velocity, relative kinetic energy corresponding to relative velocity, and there is a change in kinetic energy corresponding to peripheral velocity. These two components are here. When the air leaves this impeller, it has very high kinetic energy. Absolute velocity is very high. At inlet, absolute velocity is not high, but at the exit, because kinetic energy has been imparted to the air, the kinetic energy is very high. So, this kinetic energy is converted into pressure energy in vaneless diffuser, So, this is 1, this is state 2, in vaneless is diffuser state 3, and this will be V3, V2 square minus V3 square by 2. Then vane diffuser, similarly vane diffuser, that is 4. Then V4 square minus V3 square by 2. Then in volute casing, 5. So, then it is V5 square minus V4 square by 2. And finally, the gas emerges from here. This is the enthalpy entropy diagram for the movement of fluid in a centrifugal compressor. Now, work. How much work or power will be consumed in running the compressor? So, in order to find the energy consumed in running the compressor, we will have to draw the velocity diagram, right. Now, in this velocity diagram, the vanes are radial. This is the easiest one. When the vanes are radial, this is impeller and vanes are radial. They are like this. They are moving with certain peripheral speed or omega or rotational speed. With certain rotational speed it is moving, and omega R1, this is R1 and this is R2. So, omega R1 will give U1 and omega R2 will give U2. So, in this velocity diagram, the U will also change. Now, there is an axial entry that is like this, and blades have peripheral velocity in this direction, U, this is U. So, relative velocity will be like this. That is why this blade is curved at the bottom, so that there is no shock entry, that the fluid will slide over the surface. This is VR1, V1, and this is also velocity of flow, and this is U1, and this is blade inlet angle. This is blade inlet angle, and this is nozzle inlet angle, that is 90 degree, as we call in turbines, right. Now, if the discharge, normally in gas turbines, the radial blade type of, because RPM is very high. So, that is why the radial fan type of centrifugal compressor is used. Now, at the outlet, this is going to be the relative velocity, right, because it is radial. This is peripheral velocity U2, and this is going to be the absolute velocity V2, right, and this is alpha 2 and this is beta 2. Now, in this compressor, at the entry there is no will component, because power is calculated with the will component only. So, at the inlet there is no will component, at the outlet this is the will component. So, output is, we will first of all we will just drive the generalized equation and then we will go for the specific case. Suppose inlet also there is a will component, inlet velocity instead of it is like this. that is known as pre-will. We will discuss pre-will later on. Then torque is VW2 R2 minus VW1 R1, and when we multiply torque with omega, that is VW2 R2 minus VW1 R1 multiplied by omega, that will give the output, right, and this is VW2 U2 minus VW1 U1. Here when when there is a radial entry, this is 0, it is VW2 U2. Now VW2, this is V2 cos alpha 2 is also U2. So output is U2 square. This is the output. If you know the peripheral velocity at the outlet, we will get the power consumed or work. And the mass flow rate, because impeller has certain width, right, and the mass flow rate will always be calculated as pi d1 b1 cf1 and rho 1, because density will also change when the gas is compressed, density will be also changed. This is the expression for mass flow rate in a centrifugal compressor. Now if we take this generalized equation and we consider these velocity diagrams, now work is VW2 U2 minus VW1 U1. Now VR1 square is equal to U1 square plus V1 square minus 2U V1 cos alpha 1, that we have already done. Now VR2 square is equal to U2 square plus V2 square minus 2U V2 cos alpha 2, right. Now V1 cos alpha 1 is VW1 and V2 cos alpha 2 is VW2. Now if we rearrange these, then we will get VW2 U2 minus VW1 U1 is equal to VR1 square minus VR2 square by 2 plus U2 square minus U1 square by 2 plus V2 square minus V1 square by 2, right. Now this energy, if you remember this H5 diagram, this transmission takes place inside the impeller and this transmission of energy takes place inside the diffusers. Now there is a term slip factor which is commonly used in case of centrifugal compressors. The slip factor is when the vane, suppose there is a curved vane moving in this direction. In leading direction the pressure is high, but in trailing direction the pressure is low and sometimes wake is created, right, and because there are number of vanes, so this side there is a negative pressure, this side there is a positive pressure. So instead of leaving in this direction, the fluid tends to leave in this direction with a certain angle. So here, instead of having, in radial case, instead of leaving in vertical direction, it leaves in this direction. When fluid is leaving in this direction, definitely because peripheral velocity is constant, our V2 component will change, and this will change the vril component also, or output will be reduced. So slip factor is denoted by mu, and the value of slip factor is varies between 0.93 or 0.95. So the output is W is equal to mu u square, then mu is this one. And there is another phenomena that is known as pre-vril. Now when the air is moving in the centrifugal compressor, it is moving with a very high velocity, and it is likely in some of the cases it may exceed the sonic velocity or choke flow may take place. In order because the moment it crosses the sonic velocity, then an exit, right, the shock will take place. The shock flow will take place. So, in order to avoid that, because in that case that may damage the compressor also. It is not a desirable thing to happen. So, pre-vril is provided. So, if let us draw this ideal diagram. This is VR1, V1 and this is U1, right. So, pre-vril is this is V1. So, instead of radial entry, this angle is changed. When we change this angle, then relative velocity at the inlet is also changed, or relative velocity at the inlet is reduced, and that avoids the choke flow inside the compressor, which is not desirable. Now, regarding the slip factor, this is mu. It is the work done on the compressor, that is VWU, VW2U2, right, divided by work done on the compressor when there are infinite number of vanes. It is an imaginary situation. When there are infinite number of vanes, there is no slip. So, when there is no slip, VW2 infinite U2, and this will give this will be cancelled out. So, slip ratio is VW2 by VW2 infinite. Now, after this, we will we'll also calculate the pressure rise in a centrifugal compressor. W, we know that the W is Cp TO2 dash minus TO1. We are taking stagnation properties in dynamic compressors. Stagnation properties are taken because kinetic energy of the gas is never neglected. So, it is always taken into the account, that is why stagnation properties are taken, and the work is also mu u square by mu u square, right, and there is a factor sigma which is known as power input factor to take into account the losses, and power input factor varies from 1.03 to 1.04. So, sigma mu u square. This is, so this, the both are equal. So, TO2 dash minus TO1 is equal to mu sigma mu u2 square by Cp, right. And once these values are given, we can find that PO2 by PO1 is equal to 1 plus sigma u u2 sigma mu u2 square divided by Cp TO1 raised to power gamma over gamma minus 1. By manipulation we can find this value, because PO2 by PO1 is equal to TO2 by TO1 raised to power gamma over gamma minus 1. Now, we will solve one numerical on this a centrifugal compressor. So, quickly we will solve this numerical. A centrifugal compressor is running at 9000 RPM, delivers 10 meter cube of free air. Free air means air available at atmospheric pressure and temperature. The air is compressed from 100 kilopascal and 20 degrees centigrade. So, let us take P1 is equal to 100 kilopascal, T1 is 273 plus 20, 293 Kelvin, to the pressure ratio of 4. So, our pressure ratio is 4 with the isentropic efficiency 0.82. Blades are radial at the outlet of impeller and the flow velocity is 62. So, Vf is 62 meters per second. may be assumed throughout constant. The outer radii of impeller is twice the inner, and the slip factor may be assumed as 0.9. So, d2 or r2 by r1 or d2 by d1 is equal to 2, mu is equal to 0.9. The blades are having coefficient, the blades area coefficient of 0.9 may be assumed at inlet. Calculate final temperature of air. So, final temperature of air is, so first of all T2, as we did earlier, T2 is equal to T1 pressure ratio raised to power gamma minus 1 over gamma, and T2 minus T1 divided by T2 dash minus T1 is equal to efficiency 0.82. That will give the T2 dash here, from because the T2 we have calculated here is 435.6 Kelvin and T2 dash is 466.85 Kelvin. Many times we have done this exercise, so I'll cut short it like this, right? Then mass flow rate, free air delivered. From free air delivered, we will get the mass flow rate. M is equal to PV over RT. Pressure is atmospheric, says 100 kilopascal. Volume is 1. R is 0.287 and T is 293. And this gives the, let us take in per minute multiplied by 6. So, mass flow rate is 713.5 kg per minute. Right. So, this gives the mass flow rate is 713.5 kg per minute. So, work is mCp T2 dash minus T1. Now, we have the value of T2 dash, we have the value of T1, we have the mass flow rate, we have the value of Cp. So, work is calculated, work is 2077.7 kilowatt. This is the amount of energy which will be required to run this compressor, right? And when the blades are radial, W is mu U2 square divided by 1000. That is equal to Cp T2 dash minus T1. That is for per kg of air, and that gives the value of U2 as 440.6 meters per second. So, U2 is 440.6 meters per second. Now, we have calculated the mu, sorry U2, and now we can, because we have the ratio. So, once U2 is with us, U2 is equal to pi d2 n by 60, n is given 9000 rpm. D2 is not known to us, pi is there, 60 we know, and we know the value of U2. That will give D2 as 93.49 centimeters, and definitely D1 is going to be 46.75 centimeters. It is half of the D2. Now, V is equal to velocity of flow pi D1, sorry, volumetric discharge, volumetric inlet, volume of air sucked into the compressor pi D1 B1, velocity of flow, and Ka. This is blade area coefficient. Now, D1 we have already calculated. We have the value of Vf. Vf is 62 meters per second. This is 62 meters per second. Right? V is 10 kg per second, 10 meter cube per second. It is given here, 10 meter cube per second. So, volumetric suction 10 meter cube per second. D1 we have calculated. Vf is with us. Ka is also with us. That is 0.9. This is 0.9. And this will give us the value of B1. So, B1 is 0.122 meter or 12.2 centimeters. Now, blade inlet angle, tan beta 1. If you remember the velocity diagram at inlet, this is V1, VR1, U, this is beta 1. So, tan beta 1 is equal to V1 by U or Vf1 by U, because V1 is equal to Vf1, and that is 62 and this is U1. So, 62 U, what is the value of U? This is 440.6 divided by 2, because we have the value of U2. So, U1 is this divided by 2, and this gives the beta 1 as 0.28, sorry, 15.7. 15.7 degree. Now, regarding beta 2, sorry, now the second angle is impeller blade angle at inlet and diffuser blade angle at outlet. So, diffuser blade angle means it is alpha 3, diffuser inlet angle. So, we will take the blade angle at the outlet. So, this is the, and the blades are radial. So, this angle. So, this angle, this is this angle alpha 2, and this is going to be equal to tan alpha 2, and this is going to be the blade inlet angle for the diffuser, that is alpha 3, right. So, tan alpha 2 is equal to Vf2 divided by mu and U2. Here slip factor will also come into the picture, right, and this will give 62 divided by 0.9 multiplied by 440.6, and from here we will get the value of alpha 2 as 8.9 degree. In the coming class, we will be solving more numericals on centrifugal compressors. That is all for today. Thank you very much.